Hi everyone, I'm Stan Oda, a Senior Product Manager at Anrisu, responsible for the Shockline family of vector network analyzers. Thanks for attending this MicroApp presentation today. In today's presentation, I'd like to discuss the advantages of modular vector network analyzers, or VNAs, for some common test applications. I'll start off with a brief review of the typical integrated VNA architecture and then discuss the different levels of modularity seen in VNAs today. Following that, I will talk about the benefits of system modularity and the advantages it brings to common applications. Typical VNAs are single chassis instruments with all the source and receiver circuitry integrated in the unit. This enables lower cost components, compact packaging, and the convenience of all-in-one functionality. This type of integrated solution is optimal for well-defined applications that won't significantly change test requirements in the near-term future, like manufacturing, education, or field installation applications. A single chassis integrated architecture limits the hardware expansion capabilities of the VNA in the field, so adding ports or extending frequency coverage for future applications is not possible. Modular architectures can be classified into three major classes. Modular by chassis, where test sets and other instrument building blocks are added to a base VNA to add functionality like additional ports or increased frequency or output power. This type of modular VNA must have expansion support built into the base VNA architecture, which differentiates it from the typical non-modular integrated VNA. Modular by card, where each card is a separate instrument that is used in conjunction with a system controller and card cage, like PXIe or AXIe based instruments. Modular by standalone instrument, where separate instruments in independent packages can be configured together to create larger VNA systems without the need for a backplane or base VNA. Benefits from a modular architecture include test cost. A modular system can be configured to match current applications and upgraded later when test requirements expand. This minimizes today's equipment costs while still protecting the usefulness of the equipment for future applications. Contrast this with many integrated VNAs that have limited or no capability to be upgraded in the field. To protect against future requirements, many users buy a fully configured integrated VNA with much more functionality than is required for today's applications. This raises current equipment costs and does not guarantee that the VNA will have the functionality required for future applications. Flexibility. Modular systems enable users to configure test setups on a session-by-session basis by adding and subtracting components as needed for a particular application. This is especially valuable for high-mix testing areas like research and development labs, where a wide variety of DUTs are tested. Replaceable modules also increase uptime as faulty system components are more quickly replaced to keep the system up and running compared to integrated VNAs, which must be taken offline and fixed as a unit. Functionality. Some features and capabilities are only available through an architecture that supports modular extensions. Test frequencies into the hundreds of gigahertz and beyond can only be achieved through external frequency multiplier modules that must be supported in the architecture of a VNA. Modular VNAs can also support other functionality like optical device testing with optical to electrical, O to E, and electrical to optical, E to O, extensions. Modular systems supporting small, independent measurement modules, such as one-port VNAs, enable direct connection to the DUT, improving dynamic range and measurement stability by eliminating interface cables. Here are some examples where modular VNAs show significant advantages. Millimeter wave testing. Support for modular frequency extenders is key for this sector. Coax test port cables are no longer a viable solution to connect an integrated VNA to a device under test at these high frequencies. To effectively source and measure banded and broadband frequencies to 200 GHz and beyond, extension modules must be used to get close to the DUT to minimize insertion loss and maximize measurement stability for these applications. Multiport applications. The different types of modular VNAs, chassis, card, and independent unit, all support increasing port count beyond the capability of the typical integrated VNA to address multi-port applications. Multiple DUT testing. Card and independent unit type modular VNAs are most suited for multi-DUT testing. Both types are able to test in parallel with independent modular VNAs able to directly connect to the DUT. S-parameter testing over distance. For larger DUTs and over-the-air applications, long interconnect cables add insertion loss and instability to transmission measurements. Independent modular VNAs can act as remote VNA ports, eliminating the cable issues and extending the reach of modular VNAs to address these applications. In the next few slides, I want to touch upon a couple of these key applications in more depth. An important application example where modular architecture is a major advantage is in device characterization. Device modeling requires accurate, high-frequency measurement data to improve the behavioral predictions of models used in design. Models developed with narrower frequency sweep data sets may not predict oscillations or other unwanted device artifacts in the actual design that models developed from a wider frequency span data set may uncover. To achieve 220 GHz broadband single sweep capabilities like those available on the Anritsu VectorStar VNA, frequency multiplier modules are needed to extend the source and measure to as close as possible to the DUT. At these frequencies, it is critical to minimize the insertion loss due to interconnect length to maximize dynamic range and measurement stability that's required for these applications. Anritsu's patented nonlinear transmission line NLTL technology helps reduce the size of the modules to make it possible to directly connect to the probes used to interface to the wafer. Small modules are very important as the area available on a typical wafer prober to mechanically mount the hardware is quite limited. This can be seen in this picture of a VectorStar 220 GHz broadband setup with the small modules and probes set up on a prober. Another example where modular VNAs show benefits over typical integrated VNAs is in multiport and multisite applications. Integrated VNAs are not optimal for multiport and multisite applications since they are typically limited to 2 or 4 ports. Modular VNAs have a distinct advantage as most architectures can support more than 4 ports. Whether the expansion is supported through chassis extensions, additional VNA cards in a backplane, or additional independent VNAs, modular architectures are able to test multiport DUTs in a more efficient and economical way than integrated VNAs. Multi-site testing is also better suited to modular VNAs, as more DUTs can typically be connected simultaneously to a multi-port VNA than to a typically lower port count integrated VNA. A modular system with multiple independent VNAs can support true parallel testing to improve overall test throughput, as multiplexing VNA sources and receivers is not necessary. Measuring S-parameters over distance presents unique challenges at millimeter wave frequencies that modular VNAs can help overcome. Connecting ports on an integrated VNA to antennas in over-the-air chambers or around large vehicles for shielding and propagation measurements requires long lengths of cable. Cable insertion loss is significant at these distances, affecting dynamic range and measurement stability in these types of applications. There are solutions available to reduce the effect of cabling in these setups, but most require additional active equipment and limit setup and calibration flexibility for the application. A new modular architecture from Anritsu addresses these types of applications by making a pair of independent one-port VNAs into the equivalent of remote ports on a fully reversing two-port VNA. This new distributed two-port VNA, the ME7868A, is based upon a pair of MS46131A one-port VNAs. The MS46131A has both source and measure circuitry built into the same unit, making it essentially a completely independent VNA port. It is compact and lightweight, making it easy to move and directly connect to the DUT or measurement antennas, eliminating much of the insertion loss due to long cables in these S-parameter measurements over long distances. The modular two-port system is controlled from a central computer through a standard USB interface. So with fiber to USB extensions, a pair of one-port VNAs can be controlled remotely over a very wide distance from the PC. The key to making a distributed two-port vector network analyzer out of two independent one-port VNAs is the synchronization technology. Source and receiver phase, frequency reference, and measurement acquisition control must be handled by the synchronization scheme, which we call phase link. With the patent-pending phase link technology, the two MS46131As can be synchronized at distances of 100 meters or more to enable vector S-parameter measurements over distance without the insertion loss and measurement instability introduced by using long port cables. In summary, this has been a short discussion about the application advantages of modular architectures for VNAs. I've discussed the characteristics of typical integrated VNAs and contrasted that with features and benefits of different types of modular VNAs. I covered in further detail three different applications where modular VNAs have advantages and introduced a new modular VNA architecture that brings unique capabilities to long-distance S-parameter applications. For more information, please stop by the virtual Anritsu IMS booth or visit the Anritsu website at www.anritsu.com. Thanks for listening.